It's K and EI, and we have loading QX, and this is my X coordinate system, and this is my W positive downward. Okay. And goal indication is EI W force derivative, okay, equal to Q bar, and Q bar equal to QX minus KW, reaction force from the bottom. Okay? So the goal equation will be EI W force plus KW equal to QX. All right? And the solution for this fourth order ODE, non-homogeneous. Non-homogeneous and linear, right? Linear, fourth order, and constant coefficient, ODE. Okay? And the solution will contain two parts. One is a homogeneous solution plus particular solution, right? And the homogeneous solution will solve the EI W force plus KW equal to 0, right? And we assume, okay, plus K over EI W equal to 0, and we define K over EI is equal to alpha to the order of 4. And later on we introduce mu, right? And for this one, my solution W equal to exponential lambda x, and I will have lambda 43 plus alpha 4 equal to 0. So lambda is equal to plus minus square root I and alpha. This is my solution. Then I further introduce mu, okay? Mu equal to K over 4EI, okay, of this. Then my solution, homogeneous solution, can have various kind of form. One is A exponential mu 1 plus I x plus B exponential mu 1 minus I x plus C exponential mu minus 1 plus I minus mu 1 plus I x and plus D exponential minus mu 1 minus I, all right, x. Okay, it's 1 plus. So this is one type of solution. Another is is mu x C1 sine mu x plus C2 cosine mu x plus minus mu x C3 sine mu x plus C4 cosine mu x. Okay, or we can use the hyper sign, hyper cosine to get rid of this exponential. It's E hyper sign mu x times sine mu x plus f hyper cosine mu x cosine mu x plus g hypersine mu x cosine mu x plus h hypercosine mu x sine mu x. So we have these three types of solution. All right? Yeah. And yeah. Okay. So last time I give a solution for a particular solution where it depends on the loading, right? Yeah. Okay. Let's see. Let's see an example. If this simply support beam but on the uniform Winkler foundation, okay? Okay, so sometimes we write this way, okay? It's still spring. And it's on the constant loading, constant uniform loading, Q0. Okay? And the constants X and 0 at here. And we have a W, okay? And with EI, okay? My governing equation certainly is EI W force plus K, this is K, KW equal to Q0. So this is my governing equation. And my homogeneous solution is already got its E hypersine mu x sine mu x plus f hypercosine mu x cosine mu x plus g hypersine mu x cosine mu x plus h hypercosine mu x cosine mu x sine mu x. Okay. Now the particular solution. From this you can see, if I assume the W equal to Q0 over K by observation. Okay, if this is a Q over K, and first derivative will be 0. So certainly this term, fourth derivative is 0, satisfied. And you input the W is equal to here, K cancel K, and Q equal to Q0. So this by observation from God, okay? So you don't have to spend time to try homogeneous type solution and the undetermined coefficient, you don't have to, right? So directly by observation. Okay, this solution. So now my solution is homogeneous plus the particular solution. So my solution is homogeneous plus particular. All right? So we have 4 undetermined, and my boundary condition is what? W at 0 equal to 0, and there's a slope at 0 equal to 0. W at L equal to 0. Okay. Right. And the moment at L equal to 0. So from this 4 boundary condition, you can determine E, F, G, H. Okay? Then you got a solution. So don't do this. Don't determine this value at here. Okay? You should combine with a particular solution with a boundary condition. Okay? Because this W is not a homogeneous. This homogeneous plus particular solution satisfy the boundary condition. So you have to consider this WP is equal to Q0 over K. Okay, including your boundary condition. All right? Okay? Now, let's further discuss some fundamental solution for the beam on infinite, the infinite beam on elastic foundation with